And so really, so I guess we were thinking a lot about these things, these homotopy groups of spheres. We were also thinking about something else, which was denoted by pi st mod p star, and then maybe something else called pi st mod p v1 star. And it turned out that it was really profitable to kind of think about, and what were all these things? These were all homology theories of some ilk. And it was really profitable to think about this kind of homology theory and this kind of homology theory in order to give some sort of disproof of what the telescope conjecture was. And I think the way that Jeremy ultimately phrased this is something like, this thing after you invert something called V2 was 12 dimensional. And then it turned out that actually it was really big. And the way that we saw that it was really big was by kind of mapping into something which Jeremy denoted by the pi stable PV1 star of the algebraic K theory of something called J, which is a ring spectrum. So, and it turned out that if you sort of pass to this thing, which is maybe a priori a little bit more complicated, you can actually make some computations and show that certain things have to, not be V2 torsion, so that the dimensions of, or the dimensions of the relevant vector spaces kind of worked out how you do them. And so what I would really like to start with today is I want to talk a bit more about these homology theories, this pi stable mod P, this pi stable mod PV1, and I want to maybe give a more in-depth and sort of careful account of precisely what exactly the telescope conjecture is as phrased by Ravenel. And so to do this, we're going to have to talk about some of these homology theories. And if there's time at the end, maybe I'll say something about this thing a little bit more and how this relates to Galois descent, but I probably won't get there. And so I'll probably save some remark for the Q&A and wave my hands, and maybe this will satisfy you. But okay, let's start in section 1. So these homology theories. So maybe I'll just say more on these objects. So I think the first thing that we sort of need to say is that each of these homology theories is determined by something called a spectrum. And Jeremy talked a little bit about this in his colloquium. It's essentially it's exactly the object which is designed to represent these homology and cohomology theories that we're interested in on spaces. And so this homology theory is really coming from something that we call S, or maybe S0, depending on your sort of aesthetic preferences. And this is called the sphere spectrum. And you can sort of think about it exactly as kind of I'm starting with some spheres and I'm applying this loop suspension map that we get from that we use in the Freudenthal suspension theorem. And I'm letting that co-limit go off forever. And this is the object that I kind of get. It's something called the sphere spectrum, and it lives in some suitable category of spectra. And this is basically the most interesting object in all of stable homotopy theory. And this pi stable star thing is basically just the homotopy groups of this spectrum. You can always take the homotopy groups of a spectrum, and when you plug in suitable choices, those are legitimately sort of the stabilizations of the homotopy groups of a choice of a point in space. And okay, so what do we know about this thing? There's a couple things we know about it, thanks to a lot of fantastic work throughout the previous, well, homotopy theory is not that old, so maybe I won't say previous century, but a lot of great work was done in the 20th century, and even and amazing work has been done more recently. But maybe I'll just say one thing is that this is a ring, right? So Jeremy kind of told us how to add things together in these homotopy groups last time by using these pinch maps. But it turns out that you also have a ring structure. So one way you could kind of think about this is something like the following, is that A class inside of this object is represented by, let's say, a suspension of the sphere spectrum to the sphere spectrum itself. And if you had another class, maybe call this alpha, and if you had another class, which you could call beta or something, okay, maybe I don't want to choose these names. But if you had another class Y, then what you could do is you could suspend Y and then pre-compose in front of, suspend Y by K and then pre-compose in front of this map, or suspend X by L and then pre-compose with this map. And it turns out that those are equivalent up to a sign. And this is where we get the causal sign rule that pops up in stable homotopy theory. So this is really a graded commutative ring. I think that's the right way to say that. I always get confused about this, but okay, this is a ring. And we also know some other really interesting facts about this as well. And this is a result which I don't know where this first appeared, but probably somewhere in maybe the 40s or 50s. This is a result due to Serre from his thesis, which is pretty crazy, which is that if K is bigger than 0, then pi k of the sphere is finite. So these are all finite groups. This is, I think there's like, I can't remember the collection of people who sometimes get the phrase, the best thesis of all time attached to them, but Serre is definitely one of these people. And I think Tom is another one of these people, if I remember correctly. So this is something we know, and right away we can say something kind of fun, which is that if you take this ring and you tensor it with the rational numbers, then there's nothing left except for degree 0, which is exactly the integers. And that's a reflection of the fact that pi k of the K sphere is the integers. So this is relatively simple rationally. And another fact that we know about this is a result due to Nishida, I think from the early 70s, if I remember my dates correctly, but I could be wrong. And this is, you would love that this ring is nice, like maybe it's Noetherian or something, but unfortunately that's not the case. So it turns out that any class, so given X in pi k of the sphere spectrum where K once again is bigger than or equal to 0, X is nilpotent. And this, for example, precludes the sphere spectrum from being a Noetherian ring or something like this. Okay, so this is not looking good. We know some stuff about these homotopy groups, but pi star of the sphere is not super well behaved. However, nonetheless, you can try to undertake the study of this object, and many people have, with lots of, depending on how you define lots of, but with success at the very least. And one person who sort of undertook the study of the homotopy groups of spheres sort of early on is Toda. And so what did Toda do? So Toda found a family of elements. In say pi star S, which these days is called the alpha family, and it's usually written like this. And this lives inside of pi star S, and in work, so Toda came up with this family, and as far as I understand, it was Adams who sort of discovered a systematic way of producing all of these elements. And I don't think that this was present in Toda's work when he made these constructions. So maybe I'll just say like later, Adams gave a sort of systematic construction of this. Okay, and how did he do this? This is something that I would like to spend at least a little bit of time in depth explaining how this works, because this is sort of really critical for some of the stuff we're going to talk about later when we start discussing chromatic homotopy theory with a little bit more care. And somehow this is kind of the very first step towards the subject of chromatic homotopy theory. So here's one way that you could kind of construct this family of elements in the stable stacks. So the first thing that you want to do is, okay, so pi zero of s is the same thing as the integers. And that means, and we know that pi zero of s is the same thing as maps from the sphere to itself. And there's an element in there which is called p. And so this element p corresponds to a self map of the sphere spectrum. Okay, and one thing that you can do with spectra, which is very nice, is you can kind of do constructions you might like to do in homological algebra. You can contemplate things like taking a co-kernel or a cone, or more carefully in this case a homotopy cofiber. And there is a homotopy cofiber of this map, and you can look at the sphere mod p. And I guess I should say p is not 2 here, so that I don't have to make some annoying side remarks. But this is a spectrum, and this thing is called the mod p Moore spectrum. And it basically, this cofiber sequence here is what gives rise to this like long exact sequence that that Jeremy was kind of talking about last time. Jeremy introduced some kind of you take this homology theory, you sort of multiply by p, and then you get some other homology theory here, and then you have a long exact sequence, and this decreases the degree by 1. And so this thing here is exactly like the homotopy of, or the long exact sequence on homotopy associated to this cofiber sequence of spectra. And I should also mention kind of, maybe by analogy with something that pops up in homological algebra or triangulated categories, is that this cofiber sequence induces another map which goes to the suspension of the sphere. And what we're gonna do now is we're gonna use this map here from the sphere to the sphere mod p, and we're gonna use this map here from the sphere mod p to a suspension of the sphere. And what we're gonna do is we're gonna produce some self map of this sphere mod p, and then kind of stick the sphere and the suspension of the sphere on either side of this self map to produce some new elements. So maybe I'll tell you now, this is a theorem of Adams, which is that, maybe I'll just say there exists a self map, which I'll call V1 from a 2p minus 2 suspension of the sphere mod p to the sphere mod p. And it has the following property. It has the property that powers of V1 are not null homotopic. This is very important because, if you want to produce interesting maps or interesting elements in the stable homotopy of spheres, you better be sure that all of these maps that you're thinking about are not going to be null homotopic. Otherwise, when you try to stick a bunch of stuff together to build something, you're not going to get anything that's interesting at all. And maybe I'll just add as a remark, the way that Adams sort of shows this self map is null homotopic is basically by analyzing, Adams analyzes, and this will be a point which I will try to return to later, but Adams analyzes the effect of V1 on the cohomology theory given by, or the homology theory given by complex K. I guess, I think he does, Tyler, does he do KU upper star or KU lower star? I guess it doesn't. Yeah. All right. So the point is that Adams analyzes the effect of this self map on this homology theory, and he shows that it's not all powers of V1 are non-zero. And of course, this is like, if you are, this tells you you are not null homotopic, because if you were, then you would induce the zero map. And so this is legitimately something interesting that you can do. And so here's how you produce this alpha family that Toda found using this self map V1. What you basically do is you say, okay, I've got a sphere mod P. I know how to map into that from the sphere. And I also know how to map out of the sphere mod P into something involving the sphere. Geometrically, if you want to think about this, like this is you're sort of mapping the bottom cell of this finite complex that you have, this sphere mod P, you're mapping into the bottom cell, and then you're mapping out of the top cell. And that's the map out that you get. But anyways, what do you do? Well, you do the thing that you would sort of hope you can do here, which is you take the 2p minus 2 suspension of the sphere, you map into the 2p minus 2 suspension of the sphere mod P. You take this V1 self map or powers of it, but it's going to clutter up the notation, so I'm not going to do that. You map back down to sphere mod P, and then you map to a suspension of the sphere. And then you can use the loop suspension adjunction. You can desuspend this whole sequence, and the result that you get is a map from 2p minus 3 of the sphere, or a 2p minus 3 suspension of the sphere into the suspension of the sphere. And Adams proves that this is alpha 1, which, and here's a fact, the first p torsion in pi star of the sphere appears in pi 2p minus 3 of the sphere, and it's exactly given by this alpha 1 class. Because here, like, a map from the 2p minus 3 suspension of the sphere into the sphere is exactly a class in this stable homotopy group. Okay, and you could imagine that you play this exact same game now, but you iterate this. So I told you earlier how you multiply these elements together basically by like pre-composing and suspending a bunch of stuff. So all you do is you like raise v1 to the power of t, and this, you multiply this expression by t, you multiply this expression by t, and then what do you end up with? Let's not screw up the numerics here. It's 2p minus 2 times t minus 1. And this is the teeth element in the alpha family. And so this gives you a class in pi 2, sorry, 2p minus 2, t minus 1. And this is a way that we've now produced a family of elements in the stable homotopy groups of spheres. And well, you know, okay, we produced a family, but I made a comment about this. Is this an interesting family? It turns out that this is an interesting family. And in general, like, even if you, I think even if you check that if you produced some kind of funny like endomorphism of one of these finite spectra, and you showed that that was not null homotopic, you'll still need to check that this like composite that you get is not null homotopic. And typically to do that, you have to do some things like work inside the atom spectral sequence and execute some calculations to show that, you know, you're actually producing non-zero classes in the stable stems. And I really want to avoid talking about the atom spectral sequence today as much as I can. So I'm going to try to do that. But okay, maybe this is a good opportunity to pause and see if folks have any questions about what we've talked about so far.
Do you have any rough estimates of when is this result from?
When?
Yeah.
So Toda did this in the 60s, and I think Adams did this in, I think in his paper, he says that he knew these results from like 61, but then it took him like 4 years to write it up, so I think it's from 65.
Okay.
But yeah, I think. Does that sound right, Tyler?
Numbers.
Okay.
So I guess we would say they are classical.
Yes, this is highly classical.
Okay,
Yes,
good.
very, very, very classical. But the great news is that the fun doesn't stop here. The fun definitely doesn't stop here. And, you know, there's a V1 over here on this board. And so, you know, I don't know if you've fancy yourselves, people who like to make bets or guesses, but I think you could all kind of guess what we're gonna do next. So we have this endomorphism V1, and we had this endomorphism P. And I told you that we can take cofibers, so let's just do that again and see what happens. So maybe I'll say here, okay, I numbered things, I'm gonna stop numbering things. So Smith and Toda, independently, in, I think, the early 70s, they did basically this story, but now you do a mod V1 also. So it turns out that like, there exists a self map, and maybe I'll say, P is bigger than or equal to 5. There is a self map, which now goes from a 2p squared minus 2 suspension of the sphere mod P V1 to the sphere mod P V1. And maybe to just be really, really explicit about all of this, we took a quotient here, and the quotient that we took was, we did 2p minus 2 of the sphere mod P back down to the sphere mod P, and this is V1, and then now this is sphere mod P V1. So what do we, and then, okay, sorry, and then we also have a map from 2p minus 1 of the sphere mod P. Okay, and so we kind of have the exact same setup that we had previously. We had some kind of self map that sits in the middle here, and we could once again try to say, well, let me try to map from the sphere into now this thing, and then map from this thing out into a sphere. But now we have to be a little bit careful about the suspensions, unfortunately. So we're gonna end up with, let's see, we're gonna map from 2p minus 1 of the sphere mod P, and then this is gonna map to the 2p suspension of the sphere, where we're using this map here, and I'm adding 1. And then on the other hand, over here, what are we gonna get? Okay, can I do this in my head? No, I'm gonna look at my notes because I do not trust myself. Here, there's no problems with the suspension. So we just get sphere mod P, and then we get 2p squared minus 2 sphere, and now we have a class. And once again, this is V2 here. We could have taken powers. This is going to affect the suspensions that we see like over here, but let's not worry too much about that. And it turns out that these give rise to another collection of classes in the stable homotopy groups of spheres, which is called the beta family. So again, still very classical material, and I guess I want to say, I think it was Smith later did the gamma family. Now, of course, with sphere mod P, V1, V2, if P is bigger than or equal to 7, and so on. And so this kind of gives some like systematic collections of elements that we've produced in the stable homotopy groups of spheres. And this is really nice. Like this is maybe, maybe there's something to all this. Maybe this is a good way to try to do homotopy theory. Unfortunately, however, we have some problems with the existence of these like finite complexes that we wanted to work with. I think in 2010 or something, Lee Nave published a paper in Annals which showed some conditions under which these kinds of things don't exist, which is a little bit too bad, but we can still keep doing something like this. Okay. And so maybe the heuristic that I want to try to pitch is that when you have a finite complex with some kind of self map, you can produce new elements in stable homotopy theory. But along the way, you have to do some stuff and be really careful. You need to check things like the composition of this self map. I can repeatedly multiply this self map with itself over and over again. I want to make sure that I never get something that's null homotopic when I do that. And you have to check that. That's something you legitimately have to check. And then you also have to check the resulting classes that I've produced are not null homotopic. And it turns out that, this becomes very complicated. Okay.
Can I ask about what happens to the primes that we're slowly dropping? Because here we drop 2, now we drop 2 and 3. Is it that we don't care about those primes? Do we not need to understand those
No,
primes?
we definitely care about those
Okay.
primes. It's just that things do not go as well as, like, for instance, here with atoms, like, when you're working at the prime 2, you have to do something funny. This isn't like exactly V1, whatever that is. It turns out that it's like a power of something you could call V1. And I actually don't know so much about, like, maybe I don't know, at low primes, Tyler, are these things known to not exist, or is it just messier?
At low primes, they're known to not exist.
Okay.
That's what, yeah, like P plus, you can only go up to at most P, or less than P plus 1.
Yes, yeah, right, that's the bound from the, yeah, okay. Yeah, so, right, so non-existence, but we definitely want to understand those primes.
Mm.
Yeah, I mean, there's a reason that, in stable homotopy theory, you only ever consider one prime, or you only ever consider the odd primes. And yeah, people do both, so it matters. But maybe what I want to draw everyone's attention to before we kind of transition into the next segment of this is that there was a pretty explicit way that we checked these things were not null homotopic. We had a homology theory. And this is a homology theory which is like coming from geometry. This has to do with complex vector bundles. And so this is a relatively relatively concrete object that we can study, and we can maybe use techniques from geometry to say something about. And so essentially, maybe there are some cohomology theories which exactly allow us to detect whether or not some of these self maps of a particular type do the things that we want them to do. And this is sort of where I want to transition into talking a little bit more about the sort of big picture perspectives in chromatic homotopy theory. Okay, how am I doing? Is it 50 or is it 50 plus 10 or is it 60? I can't remember. I think it's 50.
I don't know. We also started.
Yeah,
late,
yeah, okay.
So.
Okay. Okay, so they'll say categorifying things. Okay, so as it turns out, this was not an accident. The fact that you had to work with you worked with complex K theory to check that these things are not null homotopic. In fact, there exists a collection of spectra or homology theories, if you like, called the Morava K theories. And they're usually denoted by Kn, and this is implicitly suppressing a choice of a prime P. So these are some homology theories which exist, and if you would like to know what they look like on homotopy theory or on homotopy, they look relatively similar. Their pi star of the pi star of Kn is isomorphic to Fp adjoin some map which we're calling Vn plus minus 1. So these are graded fields. The algebra over these things is really nice. So for example, if in good cases, you can make Morava K theories ring spectra. And if you look at modules over them, then their modules are relatively simple because these things are graded fields. So all modules split into sums of shifts of copies of this thing here. And just as an example, really quickly to kind of connect this back to atoms, because maybe it's not entirely clear what's going on. is if you take the spectrum of complex K theory, and you go mod P, it turns out that this thing actually splits into a sum of some suspensions of exactly these spectra here. So let's get the indices right. 0I up to P minus 2 of Y A1. And maybe I'll just write this as beta to the I, where beta is not the beta family, but rather the bot element, the bot class, which lives in pi star of KU. And so it turns out that if you like, you can view this V1 element living inside of K, or sorry, this is not an I, this is one.
The I on the top is also.
Yes. Yeah, sorry. Yeah, beta is in degree 2. Yeah. So, right. So beta lives in degree 2. And you can think about V1 as like a power of beta, in particular, the P minus first power of beta. And it turns out that, like, you know, if you wanted to if you wanted to check that some of this stuff, that these maps and these iterates were not null homotopic, you could have just as well checked on K1 instead of KU. And this is sort of where you get this summand from. Okay, but and maybe I'll just maybe I'll save this for later, actually. So more generally, I just want to sort of sketch how you can kind of construct these Morava K theories. This is going to be very vague. There's, you know, different ways you can build these things, but I'm going to tell you the way that at least I remember how to do this kind of thing. And I'm not going to tell you like a ton about all the things involved. And if you would like to, you know, harangue me with questions, I would definitely welcome that also. So how to build these things? So how do you build these things? So one way that you can build them is you can start with so we can start with something called MU, or the complex cobordism spectrum. So complex cobordism defines a cohomology theory, and this is the spectrum which represents that cohomology theory. We know a lot of really nice things about this, in particular, so work by Quillen and Lazard tells us what the homotopy groups of this thing are. It's pi star of MU is an infinite dimensional polynomial algebra on some classes that live in even degrees. So the degree of this I is 2I here. And this is a really interesting object, because this thing is intimately connected with things like formal group laws and the theory of formal groups. And it is sort of precisely this connection which Quillen observed that was maybe like the foundation for a lot of these ideas in chromatic homotopy theory. So it turns out that if you take MU, this is something which is integral. If you sort of invert all the primes that aren't P, you can show that this localized version of MU actually splits into a big sum of some suspensions of these other spectra, which are called BP, Brown-Peterson spectra. And this is essentially some sort of maybe P local, if you will, analog of MU, in the sense that, you know, and I haven't even told you what this exactly is, but the relationship between MU and formal group laws is sort of the same thing as the relationship between BP and sort of P local formal group laws. And this BP spectrum looks like this. It looks like it's, again, an infinite dimensional polynomial algebra, but now it's on some classes which we call V1, V2, and so on and so forth. And so, well, if we look at these Morava K theories, what we could think to do is, well, I know in algebra how to get from this thing to this thing here. I've got to take a big quotient, and then I've got to invert some stuff. And this is precisely what you can do with BP. You have to be a bit careful. So, you know, in general, taking quotients in stable homotopy theory is a touchy subject, but it turns out that things are okay in this situation. And what you can do is you can construct some theories, which maybe we'll call BP brackets N. These are the truncated Brown-Peterson spectra. And you can think about obtaining this spectrum by modding out BP by the ideal generated by Vn plus 1, Vn plus 2, and so on and so on. And then from here, what you can do, and of course, as you would hope, this thing has the right homotopy groups. This looks like, again, a polynomial algebra, but now infinitely many generators up to degree n. You could also, mod out this thing and kill everything up to degree n. So you could take Bpn and you could mod out by, let's say, P v1 up to Vn minus 1. And this thing is going to have homotopy, which looks like Fp adjoined Vn. And so all you have to do is you have to now invert this Vn element which lives in here. And this is one way that you could have produced these Morava K theories. So heuristically, sort of based on what I've told you about so far, is that if you want to kind of,
Is that better?
Still
We're
looking-
back.
Oh, we're back? Okay.
Yep.
Okay, so we built all of these homology theories, but like, why did we maybe want to do this? Well, the reason we sort of wanted to do this is that Adams showed us how to detect when some of these like iterates of these self maps are non-null homotopic. And in fact, one thing that you can check is that, if you take this, I guess I erased it, but if you take the V1 element or powers of the V1 element that we obtained by this construction, it turns out that the map on K1 homology induces exactly multiplication by powers of this V1 class. And so what we could kind of hope is that maybe if I've got other kinds of things like, maybe this V2 element and powers thereof, if we took the K2 homology, this would maybe hopefully induce multiplication by powers of V2. And if that's the case, then we know that that map is not going to be null homotopic because of the structure of this ring. Okay, and so the point is basically that maybe motivated by this discussion, we can kind of make a definition. So we can say, so if X is a finite spectrum, basically meaning that if you're starting with the sphere and you're doing things like, killing self maps, you're taking cofiber sequences, you're taking retracts, like things like this. If X is a finite spectrum, we basically say that a self map V from a suspension of X to itself is a Vn self map provided. Maybe I'll write this like this. So if you do the Km homology of V, there needs to be a couple of different things that could happen. So the first thing is that so this is multiplication by a rational number. if m is equal to n is equal to 0. Maybe I should have mentioned earlier that K0 is given by just the rational numbers viewed as a spectrum, the Eilenberg-MacLane spectrum associated to Q. This is an iso if m equals n is not equal to 0, and then this is nilpotent if m is not equal to n. So,
Excuse me, over there is Vn, right? Won't be Km lower star will be.
of V, yeah, because that's the name I gave you this now. Yes, I'm saying that it will be. Yes, sir. Okay. So this is what it means to be a Vn self map, and it actually turns out that if you are willing to work with powers of V, then you can ask that it literally induces multiplication by a power of the element of Vn, which lives inside of Km star, or it induces the 0 map. Because this is something that you can do. So this is what it means to have a Vn self map. And you might wonder, like, it seems like we've kind of produced some examples of these things already. We've produced kind of V1 self map, or we've produced secretly a V0 self map, which is multiplication by the element P. And then we've produced this, well, Smith and Toda produced this V2 self map. But as we've kind of seen, unfortunately, like things don't go so well if you work at low primes. However, it turns out that there's a way to kind of get around this as long as you're willing to not mod out exactly by P and by V1 and by V2, but by powers or iterates of those self maps. And so it turns out that there's a theorem. So by the periodicity of Hopkins and Smith, these Vn self maps exist, at least for certain kinds of finite complexes. And it turns out that you can give a characterization of when exactly you have a Vn self map by computing sort of some homology. In particular, you take the homology of these Morava K theories of X, and if it satisfies some conditions, you can show that X admits some Vn self map. And the way that I like to kind of draw this picture is in the following way, because this is really, I think, sort of morally or philosophically the kind of thing that you're doing when you construct all of these elements. And this is kind of what Hopkins and Smith basically do. So maybe I want to say we're going to start with the P local sphere spectrum. This has a self map called V0, which is multiplication by P. And we could do two things. We could invert P or we could mod out by P. If we invert P, we get this guy here, which is the same thing as the 0th Morava K theory. If we go mod P, well, we know by work of atoms, we do have this V1 self map, and we could have inverted that. So P mod P, and I'm going to call this T1. And I guess what do I mean by inverting here? I should say secretly what we're doing is you can view this V1 as either a self map that goes like this, or equivalently by suspending, or I guess desuspending this, you can view it as a map from X to a desuspension of X, and you could iterate that, and you could take the colimit over that whole sequence of maps, and that's what we mean by inverting. Or, we could have, so atoms here, we could have taken the following quotient. We could have gone mod P and mod V1. Here we have these V2 maps that Smith and Toda constructed for us. And so we could do exactly the same thing. We could invert V1 and get something which I'll call T2, or we could go this way and we could repeat this process forever. And the point is that you know, we're not exactly modding out by exactly V1 and P, but we're modding out by like powers of these self maps. And this is just the cleaner way to write this kind of thing. But this and this, these are called telescopes of what are called type N spectra. And you can think about type N as just admitting one of these VN self maps. And so what do we have here? We have a collection of homology theories. You know, for a fixed prime and for as we let N grow and grow. And we also have a bunch of these homology theories coming from Morava K theory. These are two collections of an infinite family of different kinds of homology theories. And one could ask, like, you know, to what extent do these kinds of things detect the same information about stable homotopy theory? And in order to say exactly what I mean by that, I need to say something very briefly about what Gauss field localization is. I'm just going to barely speak about this, but it is, in my opinion, one of the most like beautiful and nice constructions that appears in this area. Maybe not Gauss field's original arguments because they're kind of gross a little bit. You have to worry about like size and have, you know, doing small object arguments and things like this, but you know, whatever. So here's roughly the idea of what Gauss field localization is doing for you. So what you're doing is you're starting with some spectrum E, which you can think about as a homology theory. And what you can do is you can look at the collection of spectra, which maybe I'll call E acyclics. This is a subcategory of spectra, and these exactly consist of those spectra Z such that E, maybe the E homology of Z is 0, or, and by this I just mean the homotopy groups of this match product of E and C. And basically what you can do is you can take this subcategory of acyclics. This lives inside spectra, and you can take a quotient of this in some kind of way. And the result is something which you might call category of E local spectra. So E local spectra. And if you've encountered things like P completion or rationalization, these are all examples of exactly doing this kind of Gauss field localization. And what you do in those situations is you take a spectrum or an abelian group or maybe something in the derived category, and you can perform some kind of operation to it. Like when you're P completing, maybe you're going like mod P, P squared, P cubed, etc., and taking some big inverse limit. And if you're like rationalizing, maybe you're just like taking the tensor product with the rationals or something like this. But the point is you can produce these localization functors, and this also sits as inside of spectra as a full subcategory of these E local spectra. And one way you could say this is that a spectrum is E local if whenever you map from something which is acyclic into something which is local, you get 0. Orthogonal complement or something like that. And okay, so this is some kind of categorical nonsense you could do to like take spectra and like, you know, do like complete some spectra or like only look at a particular kind of information you're interested in, like the rational part, or you're only interested in like the P torsion, and so you'll go P complete or something like this. And what you can do is you can cook up some Gauss field localization functors associated to some of the homology theories that we've considered. Maybe I'll just write them like this. Ln is the Gauss field localization functor associated to the spectrum given by K0, K1, up to Kn. And then you have LNF, which is K, again, L K0. But now, instead of K1, we throw in a T1. throw in a T in. And it turns out that, if people are very interested, I can say something about this, but it turns out that there's a natural transformation, which goes from this one to that one. And there are towers involving all of these functors. You know, you have a map from, you also have a map from Ln to maybe Ln minus one F and Ln minus one. So you have something from L1 to L0 to L2, etc. And then you have something like L0F, which is tautologically the same as this one. You have L1 going to here, and then you have L2, or sorry, F, and so on. And the idea is that you've got over here like the identity functor or something on spectra. So that when you plug a spectrum into this, you get a big tower of things. And you want to try to reconstitute this like, I guess, initial term in this tower based on like all of the constituent parts. And it turns out that there is like a systematic way to measure the difference between this guy, and this guy, and this guy. And those are, maybe I'll just say, differences are measured in part by either LKN or LTN. And Ravenel in, I think, 84 or the mid to early 80s conjectured that LN is the same thing as LNF. And this is essentially the telescope conjecture. This is the telescope. And let me just say a couple things. It's tautologically true in degree 0, and it's also true in degree 1, and this is work of Haynes-Miller. So this is due to Miller. So Miller kind of proved that, you know, at height, in these degree 1 localization functors are exactly the same. And well, now, you know, because Jeremy told us so last week, we know that this is not true. This is false. Telescope conjecture is now a theorem due to Birkeland, Hahn, Levy, and Schwank. This fails. That is a gross injustice to what they do in their paper, but this is essentially like the tagline of, you know, this conjecture of Ravenel is not correct.
Do we know the force N when it fails?
Yeah, 2.
Okay, so the next
Yeah.
one is,
It fails for all N. They produce explicit counterexamples at every height. Of the
larger than 2.
Yes, all heights. They prove very specific counterexamples, yeah. And maybe I can say something about that in a minute or two here, but okay, how am I doing? Maybe, maybe what I'll close with are like 2 remarks. And maybe I can say something about why this is false. So I just want to close with 2 remarks. So for reasons which I haven't explained yet, and I probably won't get an honest chance to like legitimately explain to you in the next several minutes, there are deep connections between this collection of Bousfield localization functors and geometry. In particular, in the form of something which is called the moduli stack of formal groups. And it turns out, and essentially Ravenel like attributes pretty much the idea of building such a tower of localization functors to insights that Jack Morava had about a certain kind of filtration which exists on this geometric object. And so I think if there's a way you want to think about the difference between these 2 theories, one way is you can think that these things are very, very geometric, and perhaps techniques from algebraic geometry and number theory can be used in order to perform calculations in stable homotopy theory. And if you want a way to think about these finite localizations is, well, they're slightly better behaved categorically, but I haven't really told you what that means or why that's true. If you're interested, you can ask. And maybe the last remark is to say that the LTNs of this algebraic K-theory functor are very, very structured. And controllable or intelligible. Recently, and I guess in the past like 10 years or something, there has just been like a tremendous amount of development in our understanding of how algebraic K-theory interacts with chromatic homotopy theory, and this plays a huge role in the disproof of the telescope conjecture. People want, I can try to say something about why that's the case, but I think with that, I'll be quiet now. Thanks for listening.
Right, thanks so much. Do we have any questions or comments for the,
Yeah, I have a question.
Yeah,
So, I've seen several talks, especially by Schlack, they were talking at the Institute 3 weeks ago,
Mhm.
on phenomenal talk. So the key thing in their proof is the connection to prismatic homology. Without that, they would have been in big trouble.
yes.
Uh,
It depends on what exactly you mean by prismatic cohomology, but yeah, by and large, that's true.
okay, so can you say, just in words,
Yes.
where is this, getting into, roughly speaking, I mean, where is precisely, the connection
Yes,
which kills the thing, basically?
which makes this not go.
Exactly.
And do you want me to try to say something?
Just in words,
Yes.
don't write it.
Yeah, okay. The key point is basically that these functors here
Yeah,
satisfy Galois descent for finite groups.
okay,
They do not satisfy Galois descent for infinite groups, in particular, even for, Z or
Okay.
something isomorphic to Z. And this is the essential point of their failures. They produce an action on a particular ring spectrum, and then they show that, hey, if I compute the homotopy limit on the outside, that is different than the homotopy limit on the inside, where you're sort of intertwining the actions with this functor. This is exactly what they proved to show that the telescope conjecture fails. And essentially the point is, if you replace Tn with Kn, then that would have that kind of Galois descent that you would want to have, yeah, something of that flavor, yeah. Yes, very fascinating.
Roughly speaking, what is the Galois descent here?
Yeah, so maybe by Galois descent, I mean something like the following, so I can't remember who originally cooked up these ideas, but people took the ideas of Galois theory and adapted them to work for things like commutative rings. And then John Rognus, in the sort of, I guess, mid to later aughts or 2000s, he developed a whole theory of Galois extensions for ring spectra. And so by Galois descent, I mean something like the following. So let's say, so I can tell you what this basically means. So here, S is a ring spectrum with a G action. Let's let G be finite to simplify things. And it has to satisfy some, did I get the direction wrong? You made a face, okay.
That's a fun case.
Okay. So you have an action of G on S, and it has to satisfy a couple properties. And the properties are basically that if you take the homotopy fixed points of S with respect to G, this is supposed to be R. And then the second thing you say is that if you take this relative tensor product of, or smack product of X with itself over R, this splits as a product over the elements of G. Is it R or S, Tyler?
Yes.
Okay, thank you. So this is essentially what a Galois extension for ring spectra is. And by Galois descent, I mean the following. Let's do it in the context of exactly this functor here. Galois descent is something like if I take the Tn local K theory of my ring spectrum R, then this is actually the same thing as the Tn local K theory of S, where I've taken the homotopy fixed points on the outside. So this is like some kind of compatibility between fixed points with the chromatically localized algebraic K theory. And this is a theorem due to Klaus and Matthew, Naumann, and Noel.
So this is what you meant by doing fixed point of the action of G on the inside of that.
Exactly, yes, yeah, precisely,
That's exactly
yeah.
it.
Yeah, so see, I should have maybe written R as S fixed points G,
Yeah.
but this is what I mean by Galois.
Yeah.
And maybe just to add a really quick remark, which I think is really something that gets me very excited is that when you sort of work the Atoll topology, for instance, one way you can think about this is something like I have Nisnevich descent, which is something like excision for certain kinds of subschemes if you want. And then you have this Galois descent, which is something about the Galois action on the residue fields. And it turns out that there's like a very systematic way which you can like prove statements of the form, my functor has Nisnevich descent, and then it also has this property of Galois descent on residue fields, and therefore it's an Atoll proof. And this perspective is kind of connected to work of Bob Thomason, who produces a spectral sequence which goes from like Atoll cohomology to a localization of algebraic K theory. So that's some of the coolest work I've ever seen. So I figured I'd advertise it.
Anybody have any other questions or comments? Well, let's thank Liam again for an awesome talk.
Yeah, no problem. Good, I'm glad it was helpful. Or interesting, yeah.
Like, when you said Gauss-field arguments are gross, did you have like non-gross arguments?
No, I didn't, Tyler. I didn't have non-gross arguments in mind. It's gross no matter what you have to do. It was something you told me at one point, actually. Yeah. I believe I came into one of our meetings and I was like, I don't know why Gauss-field has to work so hard. Can't you just do this category theory nonsense? You looked at me, you sighed, you put your hands in your face and you were like, oh.
You're a jerk.
That was very cool.
Cool, I'm glad, yeah,
Conservation doesn't have that.